Greetings and welcome to Chapter 4, Section 6 of Stewart's Calculus Early Transcendentals 8th edition. My name is Matthew and I'm going to walk through these provided PowerPoint slides, which I've converted into a PDF so that we can scroll through them and write on them. And with my students, I'm actually not going to be covering this section because I'm going to focus more on the mechanical processes involved in our study of calculus, but there are some benefits to using technology and using graphing calculators or online graphing utilities, and it does give us a little bit of insight and an opportunity to talk about some of the processes that we've already looked at more algebraically or mechanically in taking first and second derivatives, setting them equal to 0, and so on. So we're going to be starting with a graph. This is not going to be a long video. We're going to start with a polynomial. It's a 6th degree polynomial. Excuse me. We will look at f prime and f double prime. And the author tells us that if we take this equation and type it into some graphing utilities, that whether we manually or it automatically decides what portion of the domain to work with. So in figure 1, we're looking at a domain or a portion of the domain that goes from -5 to +5, that the grapher will automatically select what it thinks is an appropriate portion of the range. So notice that the vertical axis here has been set to go from -1,000 to +41,000. And perhaps it automatically chose those values so that the largest amount of the graph possible would still be able to fit within the viewing window over at the right hand side at +5 on the x-axis. So this gives us an idea of what a 6th degree polynomial should look like, right? With a positive leading coefficient, it's concave up. And wow, it's really hard to tell, but look at this. This y-axis is going down to -1,000. I can't even really tell where the origin is, and I'm leaning in pretty close to try to get a look at it. I've zoomed way in. Maybe there's detail that's being lost in there. So if we change our viewing window to go from -3 to +2 in the x direction, and -50 to +100 in the y direction, we're seeing a lot more of the activity that's happening in here by the origin. And now I can tell that it looks like my curve is crossing the x-axis somewhere around -2. It looks like it's exactly at -2. And then as my curve comes up here, somewhere in here I'm changing concavity. It looks like it's hard to tell. Maybe here it looks like we're concave up on this portion of the graph, but somewhere there's a transition and it becomes concave down. And then maybe, so our function is increasing as we're moving through our x values that are going from even farther than that. From roughly here and moving to the right, our function looks like it's increasing, and then it kind of plateaus in here. If I can get my highlighter to work, it looks like it plateaus in, wow, that is a very large diameter on the highlighter. In here, near the origin, like maybe our first derivative would equal 0, so it actually might flatten out for a second there, and then the function continues increasing as we move on to the right and we're concave up. So increasing, first derivative would be greater than 0, concave up, second derivative would be greater than 0. Way more insight that we're able to draw by zooming in on this graph. So that's figure 2, and as we move down, the author makes some comments, and you can pause these and read about these if you wish. It appears to graph at absolute minimum, right? So definitely horizontal tangent line looks like it's happening in here. If you look back up at figure 2, I think we've got a horizontal tangent line there. The author is saying a minimum value, so a y value is happening at that point. I can't draw lines across pages, so coming up here, and so that the y coordinate there is approximately negative 15.33. The x value is approximately negative 1.62. And he got those values by using the trace feature on whatever grapher he is using. He says by using the cursor, was able to scroll over there and get those approximate values. And then to make some additional statements like this one that says, therefore, our function looks like it's decreasing on this interval and increasing on this interval. And that's pretty similar to what we were saying, that the graph is coming down here. It hits its lowest point at what the author is describing as an x value of negative 1.62. And then everywhere thereafter, it looks like the graph is increasing as it moves on to the right. We said there appears to be a horizontal tangent line at the origin and an inflection point, so a changing in concavity when x equals 0 and when our x value is somewhere between negative 2 and negative 1, which we were also estimating. Right, somewhere in here. We said maybe there's an inflection point there. So what we usually start with is this kind of an inspection where we're using the first and second derivatives, setting them equal to 0, chopping up the x-axis into various intervals using some test values in order to see whether our function is increasing and then changing to decreasing or vice versa, or perhaps changing from concave up to concave down. And we chop up the x-axis into those different intervals by setting either our first or second derivative equal to 0. Here, a similar investigation is done, except it's done visually, graphically, by taking the graph of the first derivative, right? We're graphing f prime here. And instead of setting f prime equal to 0, in the graph, we can go and look and see where does the graph of f prime have a y value of 0. In other words, where are the x-intercepts? And I'm seeing one here. And if we look carefully, and if we've got our viewable window set correctly, we're able to see one here and one here. So in fact, our graph has 3 different points where it should have a horizontal tangent line. We were not able to see that when we were looking at figure 2. So what does the author say about this? This confirms by the first derivative test we've got a minimum value that we found earlier, but perhaps to our surprise, f prime changes from positive to negative when x equals 0, and from negative to positive when x equals approximately 0.35. He's getting those values again by zooming in and using his cursor and tracing his way along the blue curve. So this was, excuse me, our best guess. But tough to see the transition from our slope being negative on this interval and then changing to being positive again over here. Now remember, we're looking at the graph of f prime. So the y value at this point, now I've got too many arrows. The y value at this point is 0, which means that when x equals 0, we've got a horizontal tangent line. Here, f prime is equal to 0. Look, f prime, which represents the y value. What's the y value? At this point right here, 0. What's 0? F prime is 0. The first derivative is 0. When is that happening? The answer to the question when is an x value. At which x value? That answers the question of when. The author's telling us approximately positive, what did he say, 0.35? Yep, there it is, 0.35. All right, so when we're changing from increasing to decreasing, as far as the first derivative is concerned, from being above the x-axis to below the x-axis, that means Here we're above the x-axis, here we're below the x-axis. That means we're changing from increasing to decreasing. It means that we should have a maximum at this point when x equals 0. And here on this interval we said that we are negative as far as our y values are concerned, the f prime values, so we're changing from negative first derivatives to positive first derivatives, right? All of these points up here have positive y values. So on this interval, f prime is positive, changing from decreasing to increasing, therefore decreasing to increasing, we must have a minimum. At that point, at 0.35 comma 0, no. When x equals 0.35, we have f prime equaling 0. That is not the y coordinate of our original function. That's an f prime value. It can get a little tricky when we're comparing graphs of the original function and the graph of f prime. What about concavity and inflection points? What about where we're changing concavity, therefore inflection points? This graph shows the graph of f double prime, our second derivative. And we know that if the second derivative is positive, then we're concave up, and if the second derivative is negative, we're concave down. If the second derivative is 0 or undefined, perhaps we have a change in concavity happening there. Our original function in this case was a polynomial, which is going to be smooth and continuous, so we don't have to worry about holes or asymptotes, so those kinds of discontinuities. So this is a relatively straightforward investigation that we're doing here, and let's zoom in on this graph. The fact that our second derivative up here has positive y values means that our original function f should be concave up on that interval. In other words, our original function should be concave up when we're working with x values that are less than approximately, well, what does the author say that is? Let's have some continuity here. There it is, negative 1.23. The author is suggesting for that x coordinate, approximately. So we should be concave up on that interval from negative infinity up to negative 1.23. And then our second derivative, this green graph, is negative or below the x-axis on the interval that goes from that approximate value of negative 1.23 up to, what does the author say? Approximately positive 0.19. So on that interval, our graph would be concave down because the second derivative is negative. In other words, the graph of the second derivative is below the x-axis. And then again, the graph of the second derivative crosses the x-axis. It's now above the x-axis, so we have positive second derivative values on the interval that goes from x equals 0.19 all the way up to positive infinity. So our graph should be concave up, second derivative values being greater than 0, on the interval that goes from positive 0.19 up to positive infinity. And all of that is summarized in here, so if you want to pause and jot some of that stuff down, you're welcome to. Remember that an inflection point is the point where concavity changes. First of all, when is the concavity changing? Let me grab a different color. If you look up at figure 5, the concavity is changing from positive to negative when x equals approximately negative 1.23. So what is the inflection point? The inflection point is a point that has that as its x coordinate, and the entirety of the answer to what is that inflection point requires a y value. This y value is obtained by taking the x coordinate and plugging it back into the original function f of x in this case. We don't always have an inflection point when we have a change in concavity. Sometimes there's an asymptote or a hole, and the function's not defined at that x value. We've seen that in previous videos from this chapter. So maybe go back and check those out. You can take some additional notes there. The most basic example of that is the graph of y equals 1 over x, which lives in the first and third quadrants. In the first quadrant, it is concave up. In the third quadrant, it is concave down. When does the concavity change? When x equals 0. What is the inflection point? There isn't one. Why not? Because the function 1 over x is not defined when x equals 0. So again, there's a change in concavity, but no actual inflection point. Glance back up again at figure 5. There's another inflection point where f double prime is going from below the x-axis to above the x-axis. Therefore, we've got a change in concavity there that goes from negative to positive. Change in concavity means we have an inflection point. In this case, for sure, we have an inflection point because the function is defined at approximately 0.19, and then we plugged that value back into the original function to get the corresponding y value. So this, as an ordered pair, is an inflection point, and this, as an ordered pair, is an inflection point. And that is the last slide in this set. I hope this little bit of an investigation is helpful. You should probably watch some additional videos about changing window sizes and maybe some step sizes in order to adjust the labeling of your vertical axes and vertical and horizontal axes on your calculator. Some of the online graphing utilities are just going to change the increments automatically. Your grapher will probably do it automatically. Sometimes you can change how frequently it's being labeled and so on. Also, I know that on the TI graphing calculators, investigating some of the predefined settings, I think in the TI calculators, if you hit the zoom button and, oh, I've got a TI right here. Excuse me. This is a TI 84 Plus, and if I hit the window button, well, strike that. Well, you could hit the window button and take a look at what the current settings are. Mine, is that even visible? Yep. Those are some pretty gnarly looking, I have my cursor on my face again. I hate when I do that. Those aren't really great looking values. Negative 0.3 or negative 3.3 repeating, positive 1.6 repeating. If I hit the zoom button, which is the top center, and then I hit 6 for standard, I didn't have anything typed into my y equals mode, so it didn't graph anything. But if I then hit the window button again, you'll see that this is the most brute force way of showing you this instead of like actually piping it in or using a virtual calculator or something like that. But notice that my window values are far more straightforward. My x value is going from negative 10 to positive 10. My y values are doing the same thing. There's a scale button. The x scale and y scale is set at 1. That's the kind of a value that if you change to a 2 or a 5, it would, well, I can show you. Look at the number of tick marks that are vertically and horizontally. There are a lot of them. So there's one mark for every unit. And if I go into my window mode and I change my x scale to 3 and my y scale to 3, and then I go back into my graphing window, I'm still not actually graphing anything, but you can see that the number of marks has changed. That can be convenient so that your screen is not as cluttered with as many marks. It can be inconvenient because unless you remember that you changed your scales, in this case both of them to 3, you might try to count 1, 2, 3, when what you should really be counting is 3, 6, 9. So do be careful there. So I like zoom 6 because it resets my window to all of those very straightforward settings. Another feature that I use very frequently is zoom 0. So if you scroll down, that is zoom fit, and I'm going to actually, as quickly as possible, I hit my mode button, which is below the window button. I scrolled down and went into radian mode. I'm also going to pop over into polar mode, and then I'm going to hit y equals, I had a graph in there already. This equation is r equals 3 sine 6 theta. And then I'm going to hit zoom 0 again. Oh, not zoom 0. Darn it. Don't do that. Do zoom 6 again. When I hit zoom 6, I get this graph. Notice that this graph is wider than it is tall, and I'm holding my calculator screen square to the camera. This graph should not be wider than it is tall. I also wish that the thing were zoomed in more appropriately. So the two buttons or the two predefined settings that I like to use after that are zoom 0, which is zoom fit on my calculator. And if I hit enter, what it does is it takes the graph and it fits it right into the window. Look at that. The tips of those petals are touching the borders of my screen. And then what I'm going to do is I'm going to go zoom 5, which is zoom square. And what that does is it adjusts the width and height of my window so that the image comes out looking more true. And I think you'll be able to tell now that my graph, this blue graph, is now the same width as its height. So it looks more sort of circular. Okay, it looks more like a round flower. The other thing that's happening in here, and if you don't know these little tricks from previous sections in a pre-calc class or something, you'll notice that these also look sort of like swords emanating from the center. They look kind of pointy. I don't really want them to look that way, and you can modify that by going back into your window mode, and the third setting down says theta step. So as the way that your calculator is graphing these graphs is by going and plotting a whole bunch of points, and it's starting with a theta value of 0, and then the next theta value that it's using is 0.130899969 blah 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 blah, and then it's calculating a new r value aiming in the direction of that theta value, and then it's increasing the theta value again by that same strange 0.130 amount. Unfortunately, that's not accurate enough for me, so I'm going to change my theta step to be something a little bit extreme. I'm going to go with 0.01. So now it's increasing my theta value by this tiny amount, and calculating all these new r values and plotting all these new r comma thetas. And the result of that, if I hit my graph button, is a considerably smoother, more accurate graph. It does take more time in order to generate the graph, but is considerably more accurate. So depending on the level of detail that you need, you might want to consider changing a theta step. And it's not only theta. If I go back into my mode, and I go back into function mode, and I go into my window, almost all the way at the bottom on this screen, you're seeing a delta x value. So that is the sort of level of accuracy similar to the theta step. So again, your calculator is drawing these graphs by plotting points. And almost all the way down at the bottom, there's a little delta x equals 0.035 something. That is the increment with which your calculator is increasing x values, generating y values, and plotting points. So again, if you need more accuracy, make that number smaller, but realize the smaller that you make it, the slower your calculator is going to do the graphing, the longer it will take to generate the graph. Okay, I've taken a very quick look at a section and now made it twice as long by spending a bunch of time looking at a graphing calculator. Thanks for hanging with me on this one, and join me again for the next section when I'm going to be looking at, what am I looking at next? I think we're looking at more oh, I know what we're looking at. We're going to look at some application problems. All these are definitely valuable. Trying to get the biggest bang for our buck, or maximizing the results from a certain amount of raw materials that we have. So if you would like, pop over and join me for that conversation. Thanks so much. Take care.